Okay, hi everyone. We're into our last chapter in thermo. It's a little bit different. We're going to talk about chemical kinetics. So this video will primarily have some definitions and terms. Some of them will be familiar to you, some of them may be new, but it's worth reviewing. So in general, we would define the kinetics as the study of reaction rates, right? The rates at which products are formed or reactants are consumed. And it's straightforward enough. A really good question is, well, why are we doing this, right? Why do we study kinetics? And it turns out that a reaction tells us what happens, right? So here's an example where we're making hydrogen bromide. If I take hydrogen gas and I react it with bromine gas, you get hydrogen bromide. That's what happens. Kinetics help us figure out how this happens. It's related to mechanism. And this is just one interesting example. So if I thought about this formation of hydrogen bromide, the simplest way you could imagine it occurring is called a collision reaction. So I take a bromine molecule, a hydrogen molecule, and they basically bump into each other and make hydrogen bromide. And if that were the mechanism, the rate that you would predict would look like this. It would depend on the concentration of hydrogen in bromine gas. You actually go do the measurement. This is what you find out the reaction rate looks like. It has a really, really different functional form. And so I can infer from that that whatever mechanism that's producing HBr is not this, right? So one of the main goals in this chapter is to learn how to predict, right, these types of expressions and how to get that from the elementary steps of a reaction. Okay, so how do we define reaction rates? I should write this in here. We're going to imagine some reaction of A going to B. And the way we define the reaction rate, it's given the symbol V as the instantaneous change in concentration of one of these reagents. Right? So I could imagine applying the concentration of A and it's decreasing with time. The reaction rate is just the slope of this at some point in time. Okay. You'll note that reaction rates have an expression or have a correction which accounts for the stoichiometry number of the reaction. And this is present to ensure that the reaction rate doesn't depend on the choice of reagent. The rate of this reaction should be the same if I'm talking about A or B or whatever. This is just one specific example. So this concerns the formation of nitrous oxide, NO. Here's a reaction. The formation of NO is reported as 0.16 millimoles per liter second. What's the reaction rate? Well, because this has the stoichiometry number of 2, the reaction rate is 1/2 of that number, and you end up with 0.08 millimolar per second. And then I could relate that to any one of these other species using this type of formalism. One thing I want to point out to you is that reaction rates are, in general, not constant. They change with time. So initially this has a very fast reaction rate, but as the reaction proceeds and the amount decreases, the reaction rate slows down, the slope changes. So in general, reaction rates are not constant. However, the units of the reaction rate are always the same. It's a slope. And so we're going to talk about these then in terms of concentration per second, molar per second, or some amount of stuff per second. This is always the same. All right, rate laws. It will turn out that reaction rates are often described by some formula which has the concentration of a reactant raised to some power. Let me give you an example, and I'm going to change the color of my mouse. An example might be something like this. V equals K raised to the A. It could look like this. V K A squared It could be cubed. Right? It could involve multiple species. These are all examples of rate laws. So this formulation, right, is termed a rate law. Any of these would be examples of that. The power to which the concentration is raised is termed the order of reaction. So in this case, the reactant is raised to the first power, right? So this would be a first order reaction. This one's raised to the second power. So it is a second order reaction. Last but not least, this one, what we would say is that this is overall second order. And you might say that it's first order in A. I'm going to run out of room. Yeah, or in B. Right? So that's the order of reaction. And then last but not least is this proportionality constant. Right? The proportionality constant here is termed the rate constant. So I now have reaction rate, rate laws, order of reaction, and the rate constant. I want to talk some more about rate constants. Right? Note that a rate constant is distinct from a reaction rate. Those are two different things. I mentioned earlier that reaction rates change with time, usually. Rate constants do not. They are constant at a given temperature. And you can see this a bit with units. So I'm going to imagine two different types of scenarios, a first order and a second order. Oh, my answer popped up, but that's okay. If I have a first order reaction, K going to A, reaction rates always have units of molar per second. This is equal to some unknown times concentration. Right? Therefore, K has units of 1/second per unit time. If I thought about a second order reaction, Ka squared, again, reaction rates always have the same units. It's always a molar per second. This is some unknown times molar squared. In this case, K has units of 1/molar second. So the point I want to make to you is here. Right? The units of K are not the same. They depend on the order of reaction, and they are not uniform. Right? One last slide, and then we can get into some problems. So this is an important issue, and if you're a note-taking person, I would circle this in your notes. If I give you some balanced reaction, can you figure out the rate law? A goes to B, or A plus B goes to C, or whatever. And I hope this has been emphasized to you in your general chemistry, but the answer is no, absolutely not. You cannot get rate laws from balanced chemical reactions. Reactions tell you what goes in and what comes out, but it doesn't tell you how you get from point A to point B. It doesn't tell you mechanism. And so in order to get rate laws, they have to be empirically determined. You have to go make a measurement. If you do have a mechanism, you can figure out the rate law associated with it. So we'll work on that. But just because I can theoretically devise some rate law doesn't mean that's actually what happens in nature. It's a theoretical prediction. So just because you can derive a rate law does not mean that that's necessarily what exists. And it turns out that there is more than one possible mechanism which can lead to the same rate law. So you can have two distinct mechanisms that produce the same result. And so it will turn out that rate laws can never prove a mechanism. You can only disprove them. So we'll talk some more about all these issues as we get into it. And I'm going to stop here and we'll start talking about figuring out rate laws. All right, see you next time.